let's calculate the magnetic field due to a long, but not infinite, wire. There's a bunch of stuff here, so we're just going to get started. I'm going to do this two ways. I'm going to do this the traditional way on paper, analytically, with some integration. And then I'm going to do it numerically in Python, just for fun. And so if you don't want to watch the second part, don't watch the second part. Only watch the first part. It's up to you. You make your own decisions. Okay, so here we are. This is what we're going to try to find. I have a wire with a current I in it, and I want to find the magnetic field right here. So we need to review. There's a bunch of stuff we need to look at beforehand. Number one, suppose I have a point charge, Q, moving with some velocity V. So there's a QV vector, the charge times the velocity. And I want to find the magnetic field down here at point observation location RO. So just like with the electric field, I need to find the vector value of the location of the charge. I need the vector value of the observation location, and I can get the vector value from the charge to the location. And then I have this is my equation for the magnetic field due to that moving charge. So this is mu naught over 4 pi. That's just a constant. Mu naught over 4 pi is 10 to the negative 7th. QV cross, it's a cross product. We'll deal with that in a little bit. The vector r divided by the magnitude of the vector r cubed. And some people write this as r hat over r squared. That's fine. It's the same thing. But that's for a point charge. But now here we have a current. Well, it turns out that if I have a charge QV moving this way, I can replace that with a little piece of a wire, I delta L, where delta L is the length of the wire, the tiny little piece of wire, and I is the value of the current. So this is in the direction of the current. And we have to do this because, you know, I can't treat this as one thing, right? Because different parts of the wire are different locations from here. But that gives me the following delta B, which is the magnetic field due to this little wire, is going to be equal to mu naught over 4 pi I delta L cross R over R cubed. But still, R is the vector from the wire to where I want to find the magnetic field. Okay, let's just get into this using that right there. I'm going to start over and draw a new picture. So here's my wire. Let's say the wire is in the Y, on the Y-axis, and I want to find the magnetic field on the X-axis. So this is X, that's Y. I know delta B is mu naught over 4 pi I delta L cross R over the magnitude of R cubed. Okay, so the first thing I need to do is like split this into little pieces, right? So here's my little piece right there that I want to find, and that's going to be my delta L, I delta L. And then this is going to be my observation location. So let's call this the vector RO. Let's do this the formal way. RO is going to be the vector x, 0, 0, right? If it's x distance away, then it's on the x-axis, so the y and z components are 0. And the value of this right here is going to move, so let's call that y. I'll put this as RQ is 0, y 0, right? Because it can move up and down. It can be any y value. And from that, I get R is RO minus RQ. And so RO minus RQ is just going to be the vector x negative y 0. So there's my R vector. I'm going to need that, obviously, right? I'm also going to need the magnitude of R. The magnitude of R is going to be equal to the square root of x squared plus y squared plus 0 squared, or just the square root of x squared plus y squared, because that's in the formula right there. So I got that. I got that. Now, I'm going to need to do this part right here, right? Well, let's do this I delta L cross R. So let's write I delta L vector as it's in the in the positive y direction. So I can, and this is the length dy. I can write this as the vector 0 I dy 0. Right? That's a vector in the y direction, and the length of the wire is dy. It's just a little piece. So let's do the cross product. I dl cross R, I delta L cross R. And this is the way, you can look up the formula for the cross product. I don't really care. I like to remember this as the determinant of the matrix X hat, Y hat, Z hat, and then I'm going to put my X and Y, Z components of this, which is just going to be 0, I, dy, 0, and then I'm going to put my components for R, which is X, negative Y, 0. And to find this cross product, I'm going to first expand about this row. So I get the determinant of this 2 by 2, which is 0, 0. And then I'm going to expand about this. And you remember there's a negative sign. It doesn't matter because I get 0, 0. And then the Z direction, I get 0 times that minus this times that. So I get minus I, X, dy. So that's all that is up right there. And you'll notice I only have a Z component, so I can really simplify this a little bit. The only direction value of the magnetic field is going to be in the negative Z direction. That's what I have right there, unless I get another negative sign. But it's going to be in the Z direction. So let's write this. I'm going to write this as dB. No. I'm going to write this as dB Z is mu naught over 4 pi. I delta L cross R, Z component is this. So it's negative I x dy, negative I x dy. That's that whole thing. Now I just have to divide by this cubed. X squared plus y squared to the 3/2, right? Because that's the square root and then cubed. So that's my contribution to the magnetic field due to one little piece. Notice that all of these pieces along here have a contribution in the same direction. So I don't have to worry about components of magnetic fields, which I did when we did this electric field due to a charged rod, because they all were pointing in different directions. They're all pointing in the Z direction now, so that's a good thing. Now I just need to integrate. So I need to integrate, and I can get BZ is the integral from negative L over 2 to L over 2, right? Because if this is the length L, I'm going from down here to up there. So that's negative L over 2, and that's L over 2. And then I have all this stuff. Negative, that's a negative, mu naught over 4 pi I x dy over x squared plus y squared to the 3/2. Now let's just make it look prettier. Let's pull all this stuff out front that we don't need. So as I'm adding up all these pieces, what's changing? Well, my y values are changing, right? But my x values are not. That's the location of that charge right there. So I don't have to change x. X is essentially a constant. I can pull that out front. Mu naught's a constant, 4 pi is a constant, I is a constant. So let's write this as negative mu naught over 4 pi I x. The integral from y equals negative L over 2 to L over 2 dy over x squared plus y squared to the 3/2. Now, this is not a trivial integral because, if you want to do u substitution, if I had the derivative of this up here, I don't, right? Because the derivative of y squared would be 2y dy. I don't have a y, so it's not a trivial integral. But we can still integrate. I'm going to use my math table book, which I have. I got this as an undergraduate. I'm pretty sure this is the one I have. It's the 28th edition. And, when you look through here, I'm looking for this. Forms containing the square root of x squared plus a squared. And this, I have dx over the square root of x squared plus a squared cubed, which is to the 3/2. And I know you may not be able to see that. But this gives me, and here we're talking, it has dx is my dy. So I can write that down. I'm going to just write that down. It's going to be equal to negative mu naught over 4 pi I x. And then I have plus term, I have x, which is y, over a squared, which is x squared, times the square root of y squared plus x squared. And all of that from negative L over 2 to L over 2. So now let's evaluate it at the limits. So BZ is negative mu naught I. Okay, so right here I can pull out the x squared because it's a constant. And I get x over x squared is just going to be x. So I have 4 pi over x. And then I'm going to put in L over 2. So I get L over 2 for y. And then I put the square root of L over 2 quantity squared plus x squared. And then I'm going to put in the minus. So I get minus a negative L over 2 over the square root of negative L over 2 squared is just going to be L over 2 squared plus x squared. And so here I have L over 2 minus negative L over 2. So I have L over 2 plus L over 2 is L. And then down here, these are the same, right? So that leaves me with, oh, I crumpled up my paper. That's fine. BZ equals negative mu naught I over 4 pi x L over the square root of L over 2 quantity squared plus x squared. That's that. I think that's the right answer. Okay, let's just double check, right? Because remember, dB equals mu naught over 4 pi I delta L cross R. Let's put this as R hat over R squared. And that tells me something about the units of the magnetic field. I need this mu naught IL over distance squared. So I have the mu naught IL, and then is this distance squared? It is, right? Because I have distance there, and then I have, this is going to be distance squared, square rooted, which is distance. So that's good. The units check. Units. Check. I feel like I made a mistake. Let me just double check the answer. I feel like there was a 2 there. Was there a 2 there? I did this before. Well, there might be a 2. I feel like there's a 2. Why am I thinking there's a 2? If x is... Okay, that's why. Okay. That's right. Now, what if I move really far away? So as x goes to infinity, what happens to the magnetic field? Well, down here, I have no x's on the top. So clearly, as x increases, the magnetic field decreases. And that makes sense, right? The magnetic field due to a wire should decrease. And then you could do, as delta L gets really small, this should go back over to this form. I'm not going to do that one. I'm just going to do these 2 checks. Let's do the following, though. What if x is much less than L? This is one that we want to do really close to the wire or a really long wire. Well, in that case, this term down here is essentially just x is kind of like x is 0. So I get the square root of L over 2 squared, which is just L over 2. And the L's are going to cancel, so I get BZ equals negative mu naught I over 4 pi x. And then the L's cancel, and I get a 2. So which is L over L. I'll just cancel those. Okay. And so I can write this as negative mu naught I over 2 pi x. And then often we will call this the distance r. And this is going to be negative mu naught I over 2 pi r. And that is the correct equation for the magnetic field due to a long straight wire. Okay, let's go over here and model it in Python. And then bonus, I'll show you some visualization that I made, which I'm not going to show the code for. Switching to the computer. Okay, so I already have some stuff set up. I have my magnetic constant, mu naught over 4 pi is 10 to the negative 7th. I put that in there. And then I have the current I have the length L, and then I have the x is my distance from the observation location. So let's just go ahead and start making some things here. I'm going to put my observation location, RO, is going to be equal to the vector x0, 0. Got that. What I'm going to do is to break my wire into a finite number of pieces instead of an infinite number of pieces. I'm going to calculate the magnetic field due to each piece and then add up all the magnetic fields. So I need to know how many pieces. Let's say that's 10. And then I can write my dl as the vector. That's my length, right? It's going to be a vector. I'm going to call it a vector. 0 L over n, 0. So now I can move up. It's actually a vector. And then IDL is a vector too. That's really nice. Okay, let's go ahead and make our wire, which you don't actually have to do, but I'm going to make the wire. I'm going to make a visual representation of the wire so that we can see that it's working. I'm going to start off at negative L over 2. I'm going to move up DL until I get to L over 2. So I'm going to call this RQ is equal to the vector 0, negative L over 2, 0. That's where it's going to start. Okay. And now I can say while RQ.Y is less than L over 2, do the following. I'm going to make a little cylinder as part of my wire. I'm not going to give it a name or anything. It's going to have a position equal to RQ. It's going to have an axis equal to DL. And the radius is going to be equal to L over 100. No, not 19, like that. Okay. Now let's move my value, my RQ. RQ equals RQ plus DL, and that should move it up, right? And I should get a cylinder, 10 cylinders that you won't really be able to see, but it should be there. Let's see if it works. Worked. Okay, there it goes. There's my wire in 3D. We can rotate it around. Yay. Okay, so now that I have those, I can calculate the magnetic field due to each one of those at my observation location. Let's go ahead. No, I'm not going to do that. I'm not going to display the observation location or the vector. I'm going to do that later. So what I want to do is to calculate the magnetic field due to the observation location for each one of these pieces and add it up. But I need to start with a magnetic field that I can add stuff to. So I need to start with a 0 magnetic field. Now I already have my RQ. I already have my RO. I need to find R, right? The vector from RQ to RO. So R is equal to RO minus RQ. We did that on paper. We're doing it in Python. Now I can go ahead and calculate the magnetic field due to that piece. dB is equal to mu naught over 4 pi, which is K, times I delta L cross R. Well, cross product's built in. Times cross I times DL R. Isn't that nice? Now I need to divide by the magnitude of R cubed. So divide by mag R cubed. That's it. That's my magnetic field due to that one little piece at that location. Now I just need to add that to the total. B equals B plus dB. And that should be done. Now let's print that out. Let's see if it works. And you can't even see that. I don't know why. Print B equals B. Tesla with units. Let's see if this works. There's my wire. There's my magnetic field in the Z direction, just like we said. I never told it Z direction. We get that from the cross product. Now let's just calculate our theoretical equation using the thing I have in there, and let's see if it has the same value or close. And that's only 10 pieces, remember that. So down here, I'm just going to calculate the theoretical. I'll call it BT for theoretical. It's Km times I times L divided by X times the square root of L over 2 squared plus X squared. And I already have that X, right? That was from my beginning. And let's print that. BT equals BT Tesla. Same thing. Identical. Okay, so I do want to show you, one of the nice things is to kind of visualize this field. So imagine calculating this magnetic field at different locations and drawing an arrow there. That's what I did just for fun. So this is the same wire, and this is the magnetic field at different locations. So really, you just move it around. And if you want to know how to make this code, you can. But this is a really important thing because we get this completely different shape of a field, right? It does not look like, I'm having trouble rotating around. It does not look like the magnetic field due to a point charge, right? A point charge, the electric fields radiate outwards or inwards. This is what my favorite textbook calls a curly field. It makes these curls, right? So if you put your thumb in the direction of the current, then your fingers of your right hand show the direction that these curl around. But also, as you get further away, they get smaller too. So that's a really important thing to remember when we're talking about magnetic fields, is what does this actually look like. I'll probably make a video showing you how to make this just because it's kind of fun. And this is just 10 pieces. And it's a finite length wire, so that the magnetic field over here is actually different than in the middle, but it's, legit realistic, and it doesn't go all the way to the top, but that's cool. Okay, so I like that a lot. It's kind of nice. I'll give you a link to both of these codes in the description down below, but I might make a video about how to make this just because it's fun. Okay, there you go. Magnetic field due to a wire. Hope that was useful. The end.